So in this video, we'll be going over the solutions to Lab 2 problems. Lab 2 is mainly focused on operations with matrices, so multiplying matrices together and adding and subtracting them. So before we get into the problems, we'll just quickly talk about the rules for adding and subtracting as well as multiplying. So this matrix here, just to make sure that we're all on the same page. This matrix is a 3 by 2 matrix because we have 3 rows, 1, 2, 3, and we have 2 columns. Okay, so when we're describing the dimensions of a matrix, the first number here is our number of rows, and the second number here is our number of columns. Okay, so for adding and subtracting. So for adding and subtracting matrices, the rule is they must have the same dimensions. Okay, so if I were to try and add our matrix here, so this matrix, if I were to try and add it to, let's do this matrix here, it wouldn't work. Okay, so when you add matrices together, they both have to have the same dimensions. So the only other matrix that you could add to our matrix right here is one that's also 3 by 2. Okay, now multiplying matrices. Multiplying matrices, the rule is, so let's write it out like this. We'll do another example. So we're going to just write normally what we do. So this one is a 2 by 2 matrix, and this one is also a 2 by 2 matrix. Okay, so the rule for this one is that these outside numbers, these outside dimensions, can be any number. They don't matter. But these inner numbers here, they have to be the same. Okay, so it's a 2 and a 2, so in this case we can multiply these matrices together. Okay, however, if it was, let's say we have A, B, C, D, and E, F, G, H, I, J, so we have something like this. Well, all we have to do is check our dimensions. So this one is a 2 by 2, and this one is a 3 by 2. Okay, so you can already see that right here we have a 2 here, we have a 3 here, which means that they cannot be multiplied together. Okay, so you have to make sure that these inner dimensions are the same for multiplication. So I'll just write that here. Inner dimensions must be equal. Okay, so that's pretty much it. Same thing, adding and subtracting, they have to have the exact same dimensions. Multiplying, they just have to have the same inner dimension here. Okay, so with that said, let's move on to the first question. So the first question is, we'll just call these, so we'll do it like this. This is A, B, C, D, E, and F. Okay, so we'll start on A right now. So A is asking us to multiply this matrix A by a scalar 3. So we have -3 times 1, 2, 3, 2, 1, 7. Okay, so the way that you do this when you're multiplying a scalar into a matrix is you literally just distribute the 3 amongst all of the entries. Okay, so in this case, we'll do the first entry together. So we'll go, this entry will be -3 times 1, which is -3. Then our second entry right here is just going to be -3 times 2, so -6. Our third entry is going to be -9, and likewise, we'll go through the other entries. So -3 times 2 is -6, -3 times 1, -3, and then we end up with -21. So this is our answer for A. So when you're asked to multiply a matrix by a scalar, you just multiply every single entry by that scalar. So pretty straightforward. B, we are asked to first distribute a -3, or is it a +3? Yeah, sorry, it's a +3. 3b minus a. So we're asked to go 3 times b, which is -3 to 1, and we're going to minus a. So first what I'm going to do is I'm just going to focus on doing the 3b part. Okay, so I'm going to just distribute the 3 into all of the entries of b. So I'm going to multiply all the entries of b by 3, and I will end up with this. Okay, so this gives me 3b right here. And of course the question is asking minus a. So I'm going to write out a, which is 1, 2, 3, 217. So when we're subtracting matrices, what we're going to do is we're going to take the entry in 1, 1, so 1, 1 here, and we're going to subtract the entry in 1, 1 in the other matrix. Okay, so we'll end up here. So what we're doing is 9 minus 1, so we end up with 8. Similarly, this entry 1, 2, we're going to subtract the 1, 2 entry in the other matrix. So this is -3 minus 2, so we end up with -5. And same sort of thing, we're going to take the 6 and minus the 3. So we end up with 3. And same thing down here. So you're just taking the entry and you're subtracting the corresponding entry, so the entry that's in the same position in your other matrix. So this one we're doing -9 minus 2, so -11. And then we go 6 minus 1, which is 5, and 3 minus 7, which is -4. So this is our answer for B. Okay? And C. So we're being asked to multiply AC together. Okay, so first thing that we're going to do when we look at multiplication is we're going to check the dimensions, right? So we'll write out A here. 217. Oh, sorry, that's the bottom row there. So 1, 2, 3, and 217. So A times C. And what's our C here? Our C is 1, 2, 3, 1. Okay. So first thing we do is check the dimensions once again. So this one is a 2 by 3 matrix, right? 1, 2, and 1, 2, 3. And this one here is a 2 by 2 matrix. Okay. And going back to what our rule is, we know that these two inner ones have to be the same in order for multiplication to work, but we can see in this case that they are not the same. So this one does not work. So for C, the answer is we can't do it. It doesn't work because the dimensions don't match. Okay? I'm running out of room here, so what I'm going to do is I'm going to just erase this stuff up here. Okay. So we'll go on to D now. D is asking us CB. Okay, so CB we have 1, 2, 3, 1 times 3, negative 1, 2, negative 3, 2, 1. Okay, so first thing, once again, is we're going to check the dimensions. So this one is a 2 by 2 matrix, and this one is a 2 by 3 matrix. So we check the inner dimensions here. 2 equals 2. So perfect. Now we can multiply them. So when we multiply matrix together, what we're going to do is we essentially are multiplying the rows of this matrix by the columns of the second matrix. Okay, so this just requires a lot of practice and you'll get the hang of it. It's a little bit confusing at first, but don't worry. So what we're going to do is the first entry here corresponds to us multiplying the first entry by the first entry here. Okay, so we have 3 times 1, okay, and then we're going to be adding the second entry, so this times this, okay, so that's 2 times negative 3, okay, so we have 3 minus 6, so this entry and in here ends up being negative 3, okay. I know it's a little bit confusing at first, but it will get better. So the next thing that we're going to do is we're going to multiply the second column here, so this second column, by these first two numbers again. Okay, so what we're really doing is we're multiplying this first column by the first row, I'm sorry, by this first column, and then the first row by the second column, and then this first row by the third column here. Okay, so this just looks messy now. So next thing that we're going to do is find our second entry here. So our second entry is going to be 1 times this negative 1. Okay, so 1 times negative 1 plus, then we're going to do 2 times our 2 here. Okay, so 2 times 2 plus 4. Okay, so we end up with 3. Third entry, similar type of strategy. We're taking this 1 and we're multiplying it by this first one right here, the 2. Okay, so we have 1 times 2 plus, now we're taking this 2 and we're multiplying it by this 1. Okay, so plus 2 times 1. So we end up with 4. Okay, now next step to get our 2, 1 entry. What we're going to do is we're going to take this 3 and we're going to multiply it by this 3 here, so the first one. Okay, so same sort of idea is we're taking this row and we're going to multiply it by all the columns in the next matrix. Okay, so we're taking this 3, multiplying it by the 3, so we have 3 times 3 plus, then we're taking this one, the second entry, and multiplying it by this 3, the negative 3, sorry. So we have 1 times negative 3 in here. So we have 3 times 3 minus 3, so we end up with 6. Okay? And similarly for this one, we're taking this 3 and we're multiplying it by this negative 1. Okay? So we have 3 times negative 1. And then we're taking this 1 and we're multiplying it by the 2. Plus 1 times 2. So we end up with negative 1. And last entry here is we're taking 3 and multiplying it by this 2 over here. So we have 3 times 2. And we're taking this 1 and we're multiplying it by this 1. Okay, so we end up with 7. Oh, sorry, not, yeah. So, yeah, times 1, so 7. Okay, so essentially for matrix multiplication, what we're doing is we'll say A, B, C, D here. I should use consistent bracketing. We have A, B, C, D, and we have E, F, G, H. So what we're doing is we're taking this row here and multiplying it by this column, and then taking this row and multiplying it by this column. And similarly for the second one, we're taking this row and multiplying it by this column, and then this row and multiplying it by that column. So we're taking the rows of the matrix and we're multiplying it by all the columns of the second matrix. Okay? So this is our answer right here. This is our answer for, what is this, D? Yes, for D. Okay? And AE. So we're trying to do AE. Okay? So let's write out A, which is 1, 2, 3, 2, 1, 7, and multiplying it by E, 2, 3. So let's check these dimensions. So we have 2 by 3 by 2 by 1. So we check right here, and we notice they don't match, so this does not work because the dimensions don't match. And our last one, F, is EA. So just the reverse of what we have above. So we have 2, 3, and 1, 2, 3, 2, 1, 7. So we have here 2 by 1 by 2 by 3. And once again, we look at the inner numbers to see if they match. And in this case, they don't match. So we know that this multiplication does not work. Okay? So just to recap quickly, when we add, this is so ugly. Okay, so when we add and subtract matrices, the dimensions must be the same. So I'll quickly write that down. Add and subtract. Same dimensions. When we multiply, inner dimensions must match. So that's saying that the columns of the first matrix must equal, the number of columns in the first matrix must equal the number of rows in the second matrix. And when we're multiplying matrices together, so if we have, let's say 1, 2, 3, 4, and we have 1, 2. So if we have 2 by 2 and 2 by 1, we check this, and it works because the inner dimensions work, or the inner dimensions are the same rather. And so the way we multiply this is we take all the entries from the row and we multiply it by all the entries from the column. So the first entry in the row is multiplied by the first entry in the column. So we have 1, 1. And so we have 1 times 1, and we're adding 2. So the second entry in the row, we're multiplying by the second entry in the column. So plus 2 times 2, which is 4. So it's 1 plus 4. So we end up with 5. And same thing for the second row. We're taking the first entry in the second row and we're multiplying it by the first entry in the first column. And so we have 3 times 1. And then we're adding the second entry in the second row multiplied by the second entry in the column. And so that's 4 times 2. So we have 8 plus 3. So we have 11. Okay? So the second question here, we're trying to find all of the possible matrix products that we can find. So we're trying to find essentially which matrices can multiply together based on the dimensions that they have. Okay, so first thing that we should do is we should write out the dimensions of each of these. Okay, so the first one has 3 rows and 2 columns. So this one is a 3 by 2 matrix. A is a 3 by 2 matrix. So B has 1, 2 rows and 1, 2, 3 columns. So this is a 2 by 3 matrix. And last one, this has 1, 2, 3 rows and 1, 2, 3 columns. So this one is a 3 by 3 matrix. Now an easy way to do this is to draw kind of a chart here. It makes it easy to see which products you can get. So what we're going to do is we'll label this A, B, and C, and similarly A, B, and C. So we're just going to go through and see which matrices can multiply together based on just solely looking at the dimensions. So in this entry right here, we have A times A. Okay, so A times A, we'll write it on the side here. I'm not going to draw it out, but we'll write the dimensions under it. So we have a 3 by 2 by 3 by 2. Okay, so we're going to look at the inner entries to see if they match, and they do not match. 2 does not equal 3, so we know that it does not work. Okay, so in that case, what we're going to do is we're going to put an X there. So, done the first one. Similarly, we're going to multiply A by B, and we'll write out the dimensions here. So we have a 3 by 2 by 2 by 3, and we look at the inner dimensions, see if they match, and yes, 2 matches 2, 2 equals 2, so this one works. Okay, in the same fashion, we're going to do A times C, and so we have a 3 by 2 by 3 by 3. Look for the inner dimensions. They do not match, so this one doesn't work. Okay, now we'll move on to B. And B by A. So we have a 2 by 3 by 3 by 2. Inner dimensions match, so this one is possible. Now we're doing B by B. Okay. And we have, what's B? 2 by 3 by 2 by 3. Look at the inner dimensions. They do not match, so this one doesn't work. There's no product there. So next we go B by C, and that is a 2 by 3 by 3 by 3. Look at the inner dimensions, 3 by 3. So this one works. Okay, and last one, we'll go through all the C's. So C by A, we have 3 by 3 by 3 by 2. The inner dimensions here match, so this one is possible. Let's see, we have C by B, so 3 by 3 by 2 by 3. Inner dimensions here do not match, so this one's not possible. And our last one, we'll do it over here. We'll go C by C, which is 3 by 3 by 3 by 3. And we look at the inner dimensions and notice that they match, and so that one is possible. So right here you have all of your possible products, namely the ones that have the check marks. So you have 1, 2, 3, 4, 5 possible products. So this last question is asking about linear combinations. So a linear combination, in this case, is essentially saying that you can take these three matrices or these three columns, okay, or some sort of multiple of these columns, and you'll end up with B, okay? So written in another way, it would be something like, you could go C1 plus C2 plus C3 equals B. So the reason that I left these here is because you can have some multiple of them that adds up to B. Okay, so drawing it out, it will look like 1, 2, 1 plus -2, -4, -2 plus 0, 1, 1 equals -1, 1, 2. Okay, so it's kind of like a puzzle. Your goal is to find out what these coefficients are. So what combination of these guys right here, of C1, C2, and C3, add up to B? So that's all we're doing when we're talking about linear combinations. Okay, so first thing that we're going to do is we're just going to label these as our X, Y, and Z coefficient. So these are the things that we're trying to find out. Okay, so the way that you set this up in matrix form is you're going to put these columns into the matrix. So you're going to go 1, 2, 1, -2, -4, -2, and 0, 1, 1. And it's going to equal, so we're putting it into an augmented matrix. So this should make some sense, because if you remember the last video or the last lab, we talked about our columns here represent our variables. Okay, and that's essentially what we have right here. So our X is this first column, our Y is this second column, and our Z is this third column here. Okay, and then right here is our solution. So this is our solution, what we're trying to figure out. So this is our B. Okay, so whenever you're given several matrices and a solution, and you need to find out the linear combination of these matrices, what you're going to do is you're going to put it into an augmented matrix, which just means that it has this solution part here too to it. So if it helps, you can write it out like we did here. So you write out C1 plus C2 plus C3 equals your solution, your answer right here. And you realize that these are just your variables. You want to find out your x, y, and z. So you're putting it into your matrix. So this is just another way to say this is C1, C2, and C3 and B. So you can really just put it into a matrix without concerning yourself about the x, y, and z sort of thing, but it helps later to think of these linear combinations in this way. So just like we've done before, what we're going to try and do is solve this system of linear equations. Now that should ring a bell. We've talked about it last time. Solving a system of linear equations just means that essentially you're trying to get it into reduced row echelon form. Okay? So let's do that. So the first thing that I'm going to do is I notice that I check my corner here and I notice that I have my leading one, and I'm going to use it to kill everything else in the row. So my row operations, I'm going to write them right here. So I'm going to do row 2 minus 2 row 1 so that I can get a 0 in row 2, and I'm going to do row 3 minus row 1. Okay? And you can do those separately if you want to. I'm just going to write them in the same step here. So I'm going to end up with 1. This one stays the same, and negative 1. So minus 2. End up with 0 and 0, 1, and then 3. Okay, and here 0, 0, 1, 3. So my next step is pretty evident. I'm going to get rid of the bottom row. So I'm going to go row 3 minus row 2, and I'll write it down here. Row 3 minus row 2, and so I end up with something that looks like this. So it's just going to be the same with a row of zeros here. And so what does this mean? So we see that we have our row of zeros here. We have a row of zeros. So we know already that there's going to be infinitely many solutions here. Okay. So in other words, we're going to have a parameter, and our parameter is right here. Our parameter in this case is y. It's y. Okay. So we're going to let y equal t, and t just means it's any integer. Okay, so it can be anything. So we're going to say is the element of z. So remember, this just means that t is an integer. Okay, that's all it's saying. So when we write it out as we have written it before, we get x, y, and z equals, in this case, this equals 2t minus 1, and this one equals t, and this one equals 3. Okay, and the reason that this is, I'll just write this quickly in case it doesn't make sense. So we have minus 2t, because remember t is stands for y now, plus 0z equals negative 1, and our second equation here, and we're just getting this straight from here. So this one is 0x plus 0t equals, plus z equals 3. And our last one is just a row of zeros, so we don't even have to write this one. So when we solve for x and we solve for z, we end up getting x equals 2t minus 1, and we know our y equals t because we said that right here, and our z equals, it should just equal 3. Okay, so that's where I'm getting this form here. So of course this is called the general solution. This is the general solution to our system, okay? So we scroll back up here and we notice it says it wants us to give a specific linear combination. Okay, so for a specific linear combination, you can choose t to be anything, okay, and it will just be a scalar multiple. It will just be some sort of multiple of this. So let's say you want to have t, let's say t equals 10, okay? All you're going to do is plug it in. So your x, y, and z equals your 2t minus 1, t, and 3. But in this case, if we're choosing t to be 10, all you're going to do is plug in 10 for wherever your t's are. So in this case, it's going to equal 2 times 10 minus 1 and 10 and 3. So this equals 20 minus 1, so 19, 10, and 3. So right here, this is a specific linear combination of your C1, your C2, and your C3. So another way that you could write it, how we wrote it before with the C's, we could write it as 19C1 plus 10C2 plus 3C3 equals our B. Okay, so this is an example. And of course you can choose 10 to be, or sorry, not 10. You can choose t to be anything that you want. So t can be 1, 2, 3. It can be, I don't know, it can be 3.14. It can be whatever you want it to be. So going back up here, this is what we are trying to solve. So we're trying to find coefficients in front of here that make this statement true, and we did find those. And if you want to go ahead and you want to check that out, if you want to see if 19 times this vector, or 19 times this matrix, plus 10 times this matrix, plus 3 times this matrix ends up equaling this, you can go and check that, okay?